Let's take a look at worksheet number 6. Worksheet number 6, question 8. It says object 1 has an initial charge of 1 times 10 to the minus 5 coulombs. Object 2 has an initial charge of negative 2 times 10 to the negative 5 coulombs. I'm going to circle this because it is a negative charge. We know that we're not going to plug that sign into an equation, but we know that we will have to use that sign if we have to do anything with attraction or repulsion, or if they touch each other and we have to balance them. Okay, it may be important. Object 3 has a charge of negative 3.5 times 10 to the negative 5 coulombs. 1 touches 2, then 2 touches 3, and then we want to find the force that acts between 1 and 3. So let's create our little table that shows us what the charge becomes after they touch each other. 1, 2, and 3. Number 1 has a charge of 1 times 10 to the minus 5. 2 has a charge of negative 2. And 3 has a charge of negative 3.5 times 10 to the negative 5 coulombs. All right. So now what happens? 1 touches 2. Let's circle those. Okay, some of you, as you're doing this stuff, try to take shortcuts. Okay, like, you think you're so smart that the shortcuts, like, you're not. You're not that smart. You're not that smart that you can take all these shortcuts. Either am I. Okay, none of us are. When we try to take shortcuts, that's when we start messing up. When I make a mistake on an answer key, and it happens sometimes, I make a mistake on a quiz answer key or an assignment answer key or something like that, it's always because I was trying to do it too quick, taking shortcuts. Okay, we make mistakes when we take shortcuts. Do everything like this. You got tons of time to write a test, especially an exam, right? Tons of time. There's no worries about time at all. Write things out. You're less likely to make mistakes, just like I'm less likely to make mistakes when I write things out. So this is what we do. We circle 1 and 2 because they touch each other, and then we figure out what they become. 1 and negative 2 gives me negative 1. Divide by 2 because we balance them out. We get negative 0.5. And this one stays at negative 3.5 times 10 to the minus 5, of course. And then it says 2 touches 3. Circle those ones. 2 touches 3, that gives me negative 4 when we add those up. Divide by 2, and that gives me negative 2. And this one is 0.5 times 10 to the minus 5. And now we want to find the force between 1 and 3. So the force between this guy and this guy. Now it's easy, right? F is equal to K Q1. I'm going to say Q3 because we're dealing with the first charge and the third charge. It doesn't really matter what you call them, though, over R squared. So we're going to say 8.99 times 10 to the 9 times 0.5, drop the sign of the charge, times 10 to the minus 5. That's not in scientific notation. 5 times 10 to the minus 6 would be scientific notation. But, what's the difference? This way, if I write it down this way, it eliminates the possibility of me making a mistake moving the decimal place over, right? Okay, I move it over one place, 5 times 10 to the minus 6. What if you move it the wrong way and say it's 5 times 10 to the minus 4? Well, then you're wrong. If I just leave it here, 0.5 times, well, that's good, no threats. Okay. All right, second charge here, the third charge is negative 2. Actually, we're going to drop that negative, right? Never plug the sign of a charge into an equation. 2 times 10 to the minus 5 coulombs divided by the distance, which is 2 times 10 to the minus 3. Now, I'd pull this up on the calculator, but my calculator isn't working right now. So I'm going to trust that you can get the answer here. Do the math. Make sure that you can get the answer that I have here. If you can't, please let me know. I end up getting 2.25 times 10 to the 5 newtons. Good? Yep.
I'm sorry, for number 7, what was the answer?
For number 7, the answer was 2.88 times 10 to the 13 newtons. So we're going to do that one in number 7, essentially the same way. Ends up being a little bit easier because you don't have those exponents for the charges. But other than that, it's the same question. Yep.
Why do you have 3 charges at the top?
Why do I have 3 charges at the top? Because object 1 has this charge, object 2 has this charge, and then object 3 has this charge.
But it's asking for the electric force that acts between charge 1 and
Yeah, that's right. But 1 touches 2, so the charge of 1 changes. So I have to figure out what it becomes. And then 2 touches 3, so I have to figure out what 3 becomes as a result of that touching. The final charge on 1, 2, and 3 are these. Now, who cares what it is on number 2 afterwards? Because it's still the force between 1 and 3. This one's irrelevant now, but we found it as we were finding the other ones. Okay, in the end, it's still this one and this one that matter here. Okay, does that make sense? Let's try another example here. This was number 3 on your sheet. It says, find the net force on sphere B due to spheres A and C. So this is A, this is B, this is C. Find the force on B due to A and C.
It just mirrors just no one else has this.
Now, what's the strategy for this? Well, the strategy for this is real similar, believe it or not, to what we did in Physics 20 a number of times. Remember in Physics 20 we had those elevator problems? Remember in Physics 20 we had those inclined plane or hill problems? We had those vertical circular motion problems. Okay, what's the force of the track at the top of the loop? Or we had all kinds of problems in Physics 20 where we had multiple forces acting. That's exactly what we have here. It's just that these multiple forces are both electric forces. So let's draw a free body diagram. Let's draw a free body diagram. On object B, because that's what we're trying to find here, right? The net force on B due to A and C. Now, there is a force on B caused by A. Forget about C. Pretend it doesn't even exist. For now, we'll come back to that one in a second. Okay, there is a force caused by A on B. Which way does it act? Well, somebody said it was repulsive. Why is it repulsive? Yeah, because they're positive charges, right? Positive and positive repel each other. That means that A and B are going to push each other apart like this, right? If this is A and this is B, then A ends up going to the left and B ends up going to the right. Now, I don't really care what happens to A. Yeah, it gets pushed to the left, but that's not what I'm trying to find. The question here says, what's the force on B? So let's ignore that one. Let's pretend that one's not even there. Doesn't matter. The force on B caused by A is to the right. Agree with that? Because B is pushed away from A as a result of that repulsive force, the repulsion between positive and positive. Now, let's pretend A isn't there anymore. Of course it is, but we'll pretend for a second that it isn't. B and C, we got a positive charge and we got a negative charge. Are they going to attract or repel? They're going to attract, yeah. So what happens to C as a result of that? Two-word answer. What happens to C as a result of that attraction force? The answer is, the two-word answer is? Okay, I was going to say who cares, but that's close. Don't care. We don't care. It doesn't matter what happens to C. If the question said what's the net force on C, then we would care. If it says what's the net force on B, it doesn't matter which way C moves as a result of that. Okay, let's look at my hands here. My right hand here is representing B. My left hand is representing C. If that's an attractive force, which way does B go? It's attracted to C, it goes to the right. So we're going to say that the force on B is also to the right. They're both to the right. Now, there won't always be both to the right, right? Sometimes one's going to be to the left, one's going to be to the right. But in this case, they're both to the right. What comes next? You can do this. What comes next? Rachel? Oh, sorry. Sorry. What comes next? Yeah, calculate the force. Regan said we're going to calculate the force, both of the forces actually, right? Rachel, Regan, R squared, that's a statistical thing. Statistically, we'll get it right 50% of the time, right? There you go. There's always a tie-in. So Regan says we're going to calculate both of these forces here, KQA, QB over R squared. We're going to say that's 8.99 times 10 to the 9 times QA, which is 2 times 10 to the minus 6, times B, which is 3 times 10 to the minus 6, over the distance, which is 2.00 meters squared. Let's calculate that force. And I think when we do, I think we get 0.01345, is that right? Now we find the value of FB, the force between B and C. We're going to say K QB QC over R squared. Okay, we sub in the numbers for that. 8.99 times 10 to the 9. QB is 3 times 10 to the minus 6. QC is 1 times 10 to the minus 6. And the distance is 1.5. And we solve for that one. And that one works out to be, I believe, 0.01198 newtons. Is that right? Now what are we going to do with these? Add them up. Yeah? F net is equal to the sum of the forces. Like we did in Physics 20 a million times. FA plus FB. Now in Physics 20, we usually said F net was also equal to M times A. Right? MA is equal to the sum of the forces. But here, since we're just trying to find the net force, not the acceleration, we'll just say FA is 0.01345 plus 0.01198 newtons. Now, what would happen if, let's say, the force of C on B, I should have called this FC actually. Just noticing that now. Do you see that? I should have called it FC, indicating that it's the force of C acting on B. Okay, what would have happened if FC had been to the left? We would have made a negative. We always add forces together to get the net force, but we would have made one of them negative, right? Look, if I include the negative charge right here, right, this is a negative charge, right? If I include the negative, then I'm going to get a negative value for force there. But yet when I sub it into this equation, it has to be positive. Now you can see maybe why I don't want you to plug the sign of a charge into an equation. It's just going to lead to confusion. If I plug the signs into an equation, you're going to get a positive here and a negative here, and then you're going to add this plus negative this, and you're going to get the wrong answer because they're both to the right. Yeah. So we add these up. We add these up and we get 2.55 times 10 to the negative 2 newtons. And of course it's positive, which means it's to the right, which you know it's going to be when we have two forces that are acting to the right. Okay, let's take some time now to work in class at worksheet number 7, questions number 1 and 2. 1 and 2 only for now. Let's have a look at 1A here. It says 3 charges are in a straight row. The first charge is 5 times 10 to the minus 5 coulombs. Let's call that number 1, and let's make it 5.00 times 10 to the minus 5. And then it says there's a second one that's to the right of the first one, so we'll call that one conveniently object number 2. It's also 5.00 times 10 to the minus 5 coulombs. And then there's the third one over here that's negative 2.50 times 10 to the negative 5 coulombs. Distance is involved here. We get 2.50 centimeters, and we have 2.00 centimeters. So that's what we call that a situational diagram. That's what my situational diagram should look like. When I start adding forces, it becomes a free body diagram. Now, we're looking in question A for the net force on object number 1. So let's look at the two forces separately from one another. 2 acts on number 1. They're both positive, so they're going to attract or repel. Well, they're going to repel, right? So 2 gets pushed away from number 1. I was calling it F1 before, the force of 1 on 2. I'm going to call it F12 here right now because as I was talking to somebody walking around here, that made more sense, okay, when I call it F12. So it showed whoever it was, I can't remember who it was, but it showed that person that it's the force of 1 on 2. Doesn't really matter what you call it, though, as long as you understand what it represents. Now, 3 and 2 also apply a force on each other. Is that attractive or repulsive? It's attractive because they're opposite charges. So that as a result of that, 2 is going to be pulled towards number 3. I'll call that one F32, the force of 3 on 2. 2 is pulled towards number 3. 3 is pulled towards number 2, but I don't really care because I'm not trying to find the force on number 3. Not yet, anyways. Let's calculate both of those forces. F12 is K Q1 Q2 over R squared. And you got to be careful here. Not too bad, but you got to be careful to make R in meters, 0.0250 meters. Q1 is, both of these guys, in fact, are 5 times 10 to the minus 5 coulombs. Gives us a force, F12, of 3.596 times 10 to the 4 newtons. Now, if I calculate the other one, F32, we're going to say K. We're trying to find the force on the first one here, aren't we? Okay, we're doing B here now. Let's pretend we're doing B. Make sense? So I don't have to change everything that I just have there. So we're finding the force on the middle one here. K Q2 Q3 over R squared. Okay, you know what Q2 is, you know what Q3 is. R is 0.020 meters. Okay, we solve for that force, and it works out to be 2.8094 times 10 to the 4 newtons. Now you go to add them up. We say F net is equal to the sum of the forces, F12 plus F32, or whatever you call them. We add them up both as positive values because they're both acting to the right. And when we do that, we get 6.41 times 10 to the 4. Now, if you were looking for the net force on number 1, let's say you were looking for the net force on number 1. Number 1 would be pushed this way as a result of number 2. We'll call that F21, and number 1 would be pulled towards number 3. We'll call that F31. What would you have to be careful of when you're finding F31? The force of 3 acting on 1. It's negative, so when you add them together, well, it's actually positive force. It's a negative charge, but it's positive force. We add them together, F31 is positive, F21 is negative. But what's the other thing you got to watch out for? I think Kenny might have said it. Yes. When you're finding F31, KQ1, Q2 over R squared, R for F31 will be 0.045 meters. We've got to add those distances together, right? You see why we do that? We want the distance between 1 and 3 to find the force of 3 on 1. And that distance is 4.5 centimeters converted to meters. All right, I want to do one more example with you, and then I'll let you work for the remainder of the day here. The last example is, well, similar to what we just did as our example a few minutes ago, but same numbers. But now you can see that this is a two-dimensional thing. First step is going to be do the same thing as we did before. Draw a free body diagram. A pushes B this way. Now B pushes A to the left, but we don't really care about that. It's a repulsive force here. B is pushed away from A. B and C, negative and positive, that's an attractive force. That means that B will be pulled down towards C. So the force of C on B is a negative value. It's a downward force. We calculate both of these forces. The good news is I just calculated both of those forces. FAB from the previous question that I just did, FAB ends up being 0.01345 from the previous example, and FCB ends up being equal to, from the previous example, 0.01198 newtons. Well, we still got to add them together. Remember this example? We had those two forces. We added together like this. Okay, how do we add these forces together now? A triangle, right? A vector diagram. FAB we'll say is 0.01345, and we'll say FCB is 0.01198, and the resultant vector, which is the net force, that's what we're trying to find, is just the Pythagorean theorem there, the square root of 0.01345 squared plus 0.01198 squared. And then theta is equal to the inverse tan of opposite over adjacent. Opposite 0.01198 over adjacent 0.01345. We do this one for the force. We get 1.80 times 10 to the negative 2 newtons. Anybody else get that? Yes? And the angle works out to be 41.7 degrees. Now, for the angle, we're not going to say south of east here. We're just going to leave it as 41.7. How come I'm not going to put in south of east here? Yeah, like the Earth is not our frame of reference here. It doesn't mention anything about north, south, east, west. So there's no reason to put south of east here. We just got to say it's 41.7 degrees and make sure that we have on the diagram labeled where it is that we've calculated the angle. That's the best we can do for that. All right, so I'm going to ask you to finish that worksheet now, questions 1 through 4. Questions 3 and 4 are on questions like this. In addition to that, I'm going to ask you to do practice question set number 10, which I believe only involves 2 multiple choice questions. You still got the rest of class to work on this, almost another 10 minutes. And remember that as you get further along through these questions on the worksheet, it becomes less and less work because you've already done a number of the calculations. So it shouldn't be an onerous amount for you.